So good afternoon everyone. So welcome to my YouTube channel Math Theorem. So today we are going to see very important theorem that is called Weierstrass Approximation Theorem. We will also do two problems by help of this theorem. Okay. So Weierstrass Approximation Theorem. Okay. Let f be a continuous real valued function defined on a closed interval AB where AB belongs to R such that A is strictly less than B, then there exists a sequence Pn of polynomials converging uniformly to F on AB. Okay. So let's see its proof, how it will work. Okay. So we know that that hx function, hx, I am taking hx is equal to x minus a upon b minus a. So this is x. Okay. So h function is from closed interval AB to closed interval 0, 1. So this is a bijective continuous map. It means we can change our interval AB to 0, 1. So we can assume that our function f is defined on closed interval 0, 1. Ultimately, we can interchange. We can take composition, then we can take inverse by h inverse. So ultimately, it will not affect our proof. So we assume that f is defined, okay, on closed interval 0, 1. Okay. So it is defined on closed interval 0, 1. Another thing you observe that if I am taking capital X is equal to fx minus f0, okay, f0 minus x f1 minus f0, okay, then fx is approximated uniformly by a sequence of polynomials if and only if f is approximated uniformly approximated uniformly by a sequence of polynomials. It is very clear. Suppose we have polynomial which approximates f. I can take this part, I can add this part, this much part, f0 minus f, then that will approximate uniformly f. Okay. And conversely, if something is approximated f, I can subtract this part, that will approximate capital F uniformly. So it is obvious. Okay. Also observe here that f at 0 is 0 and f is equal to 1. Okay. Okay. This quality is also satisfied. At 0 is 0 and 1 1. Okay. So without loss of generality, we can also assume that our f satisfies this condition. So we also assume that our f satisfies this. Okay. Next, we consider b and t is equal to, one thing. Now, we want to extend our f to whole real line because our f is defined on this interval. So we have f 0 1 to r such that f0 is 0 f1. But our function is not defined outside closed interval 0. So we define. So our f we define f does not belongs to 0 1. Sorry. So we write here, we extend f, okay, on R by defining fx is equal to 0 for all x belongs to R such that x does not belongs to closed interval 0 1. Outside closed interval 0, I am saying my function is 0. So now we are not changing notation. Still we are saying f is f. Okay. Extended function is f. So now f is continuous on R. Okay. Now f is continuous on R. Now we write b and t is equal to cn 1 minus x square to the power n, or n is equal to 1, 2, 3, up to. Here cn is greater than 0. Okay. Okay. Now observe that for x mod less than equal to 1, we have that Bn is non-negative. Bnt is non-negative. So here not xt. Okay. Non-negative. Okay. Also, okay, we set Cn such that integration -1 to 1 Bnt is nothing but on this interval is nothing but 1. We are taking Bnt, we set which are in this form, Cn is greater than 0, and if we are taking in this form, obviously when t is less than equal to 1, it is non-negative. We set Cn such that this satisfied. Okay. Now we want to find a bound for Cn. So 1 is equal to -1 to 1 Bnt dt. Okay. So if we take a smaller domain, because in this domain, so we can also write -1 to 1. Cn will come out. So 1 minus x square and dt. T square dt. Okay. So we are taking a smaller domain, minus 1 upon under root and 1 upon under root. Then integration will decrease because this is a non-negative function. 1 minus t square and dt. So we solve it. What we'll get? By binomial theorem, here I can take x because I have taken function in variable x. Okay. So I will take x here, not t. It will not affect anything, but I am taking x. Okay. So p and x is this. Now this is 1. So Cn will come out 1 minus x square to the power n dx. Okay. Now if we take a smaller domain, because -1 to 1, 1 minus x square is a positive function, non-negative function. So we can take a smaller domain, the integration will decrease, Cn is positive. So this is even function. So we can write as interval is symmetric -1 upon under root n to 1 upon n. So we can write like that. This is property of even function. Okay. Now by binomial theorem, 1 minus n x square is less than equal to 1 minus x square. By binomial theorem, so it will be still less than 2 Cn 0 to 1 upon under root n 1 minus n x square dx. Okay, now solve this. X minus n x cube upon 3 0 to 1 upon under root. Okay, so by solving this, what you will get? 2 Cn, you will get 2 upon under root n, you will get after solving this. Okay, putting the value upon 1 upon in place of 1 upon under root, then 0. So this is 4 Cn, 3 will come outside. 2 upon 3 into So it will be 3 by 1 upon under root n. Okay. But 4 upon 3 is greater than 1. So if I write 1 in place of this, this will be this. So finally what I got, I started with 1 is equal to minus 1 to 1 b and x ds. So this satisfies. So I have, so Cn is less than, Cn is less than, we got this bound. Okay. Now b and x is equal to Cn 1 minus x square, and that will be less than 1 minus x square. Okay. On closed interval minus 1 to 1. I am taking restricting myself. Okay. So for any fixed delta greater than 0 such that delta, so for any fixed delta with delta in this range, we have b and x is less than under root 1 minus delta square n for all x belongs to minus 1 to 1 such that okay. Now observe that this do not depends on x, and this tends to 0 as n tending to infinity. b and x tends to, this is less than 1 minus delta square, that tends to 0 as n tends to infinity. And this expression do not depend on x. This implies b and x tends to 0 uniformly on this interval. Sorry, I have written wrong. For all x belongs to such that delta is satisfy this. So Bn tends to 0. So Bn tends to 0 uniformly. It means converges uniformly on this interval. What is this? Minus delta, sorry, minus 1 to delta. This is what? This is, what is equal to this? Which value? Which interval? Minus union delta to 1. So Vn tends to 0 uniformly. Now, okay, we define P and X is equal to minus 1 to 1. We define for 0, X to 1, P and X is equal to minus 1 to 1. Okay. So we should write properly. For X in this range, we define P and x is equal to fx plus t b and t dt. Now what is b and t? Sorry, p and x is equal to this. I can break in this form. -1 to x minus x fx plus t b and t dt plus minus x to 1 minus x fx plus t b and t dt plus -1 to x 1 fx plus t b and t dt. Okay. This part, we will show that this integral is 0 and this integral is 0. Why this is 0? Because if I am taking this interval, what is on this interval? On -1 to minus x. What about this fxt? What about this on x? If I put lower value of what I will get, 1 minus, sorry, x minus 1. And if I put maximum value of t here in this subinterval, x minus x, that is 0. Okay, it means x plus t value is less than 0. And we know that when x plus t value, sorry, when I'm taking x less than equal to 0, outside outside 0, 1, close interval, f is 0. It means if we take x less than equal to 0, my fx is going to be 0. So x plus t is less than equal to 0. It means fx plus t is 0 on this subinterval. So that is why this part is 0. That is why it is. Similarly, if you see that, similarly, on -1 minus x to 1, I should write we have here. We have x plus t. What is this? I will put minimum value 1 minus. So what I will get? This is 1. And what about x plus 1? So its lower value is, lower bound is 1. Outside all the value of x greater than 1, my fx is 0, but x plus t is also greater than 1. So this implies fx plus t is 0 on this subinterval -1 to. That is why this part is also 0. Okay, this part. These two integrals becomes 0. So what I got? I got p n x is equal to minus x to 1 minus x fx plus t x plus t b and t 30. If we change the order, sorry, if we change the variable, suppose I am taking x plus t is equal to y. So what is my t here? Y minus x. What is dt is equal to minus or dy. So what is, when the limit of t is x, it will be 0. When limit of t is this, I will get this. So I will put y, b and t, y minus x dy. Okay, now it is changing, it changed to this end. But still I have changed this in the y. Still I can, so this implies p n x is equal to 0 to y f y b n y minus x dy. Okay, So I got this one. So I got this one, x plus t, I have taken y, and I have dt is equal to dy, dt is equal to dy, and I have changed it in this form. Okay. So then finally this integration, when the variable, when I will take integration, okay, when I will take integration, then when I will take integration, y variable will be disappear, okay, disappear. So certainly this is going to be a polynomial because bnx is a polynomial, okay. So when I will take integration, then fy will not affect the polynomial this, okay. It will take integration. So this is integration, and y variable will be disappear later. So this is actually polynomial. So it is proved that this is polynomial. So this implies Pn is a polynomial on, okay, this is a polynomial on -1 to 1, okay. So this is a polynomial on 0, 1, because this is fy, when will, and this is Pn, this is a polynomial, okay, but integration is with respect to y. So after solving it, it will be a polynomial, okay. So Pnx is a polynomial. Now we will show that Pnx tends to f uniformly, okay. Now since f is continuous on 0, 1, okay, so f is uniformly continuous on 0, 1, okay, okay. So let epsilon greater than 0, there exists delta greater than 0. We can manage delta so that delta do not exceed 1. We have, by definition of uniform quantity, we can choose lesser delta, okay. Fx1 minus Fx2 less than epsilon by 2 for all x1, x2 belongs to closed interval 0, 1 with x minus x2 absolute value is less than delta, and this is less than equal to 1 because delta is less than, okay. Okay. So now also f is continuous, is bounded, so bounded on closed interval because every continuous function on a closed interval is bounded. Every continuous function defined on a closed and bounded interval bounded. So there exists m greater than 0 such that fx less than m for all x belongs to 0. Okay. Now what is fx minus p and x? Now for x we have, okay, so I can also write this in this, no problem. Okay, so what is this? Minus 1 to 1 f x plus t b and t dt minus fx. Okay, but minus 1 to 1 fx plus t b and t ft, because minus 1 to 1 b and t dt is 1, so it will not affect anything if I'll write this. Okay, now what is this now? Minus 1 to 1 fx plus t minus ft p and t dt. Okay, that is less than equal to fx plus t minus ft p and t. B and t is non-negative in this range, minus 1 to 1. So no need to write absolute. Okay. 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 Sorry, I should not write here. One thing I made mistake. Because we have extended continuous on R. F is, because outside 0, 1 it is, outside 0, 1, so one thing. It is correct, okay? No problem. 0, 1. There is a problem. No, there is no problem. Actually, I want to say one thing. Because outside, so F is bounded on R. Because why F is bounded on R? Sorry, one thing. F is bounded on R. Okay. So F is bounded on closed interval 0, 1. But outside closed interval 0, 1, F is 0. This implies what? That because outside closed interval 0, 1, F is 0. So I can write this F belongs to R. Because ultimately it is going to 0. Okay. So I can write like that. Okay. So now I can break this integral in 3 parts. Minus 1 to minus delta. Okay. F x plus t okay minus ft b and t dt plus minus delta to delta fx plus t minus ft b and t dt. Okay, and then next integral delta to 1 fx plus t minus ft b and t dt. Okay, so this part is bounded by 2m. Okay, bounded by 2m because fx is bounded by m. So this part is bounded by 2m. So I can write 2m in place of this. 2m will come outside. This part is also bounded by 2m. Okay, so minus 1 to minus in p and t dt. Okay. Now what about this? In this, the difference is huge uniform continuity. We have told that x plus t difference is x. X is less than equal to delta because, okay, okay. Sorry, here no t. Actually, there is f x. I made a mistake. This is fx here, no t. This is fx. This is fx. So I am writing fx here. So this is fx. Okay. This is fx, 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 fx. Okay. So I have written fx. Okay. Now what about this third integral? Third integral is also bound. This part is bounded by 2m. It will come out 2m by replacing this in place of replacing 2m in place of this fx plus t minus fx absolute value b and t dt. What about second integral? Because if you take x plus t difference with x will cancel out t, and t varies minus delta 2. Now we can use uniform continuity of f on 0, 1. So this will be less than epsilon by 2. Epsilon by 2 will come out. Okay. So what we got? I can take 2m common. So I will get minus 1 to 1 minus delta b and t dt plus delta to 1 b and t dt. Okay. And what about this? Epsilon by 2 minus delta to delta b and t dt. Okay. But I know that b and t 2m minus 1 to delta minus delta. B and t is less than under root 1 minus x square n So the t here, t dt. Okay. Sorry, 1 minute. Okay. But I know that this part is less than, so 2m. This part -1 to the end. Bnt is less than under root n 1 minus delta square to the power n dt. Okay. Similarly, delta to 1 under root n 1 minus delta square dt. Okay. So this is less than. And what about this? I can take bigger interval dt in place of this integral. Okay. So what we will get here? 2m under root n. This is constant thing. Okay. So minus 1 to minus delta dt, delta 1 dt. And what is this? This is 1. So this is epsilon by 2. Okay. So after solving it, what you will get? This part, what you will get after solving? It will come to 1 minus delta. This is 4 times 4m minus delta under root 1 minus delta square to the plus the epsilon by 2. Okay. Okay. So now delta is in between 0 and 1. So if I skip delta here, it will increase 4 times m under root n 1 minus delta square n plus epsilon by 2. Okay. So I have this fx minus p n x for all x belongs to closed interval 0, 1. Okay. Now let's say it's equation number 1. Now delta, this part 1 under root n 1 minus delta square n tends to 0, implies there exists n belongs to n such that 4m, because m is fixed, 1 under root 1 minus delta square to the power less than epsilon by 2 for all n greater than equal to n. Okay. So I am saying this equation number 2. From 1 and 2. From 1 and 2, we have fx minus pnx is less than epsilon by 2 plus epsilon by 2, that is epsilon. This implies fx minus pnx less than epsilon for all n greater than equal to capital N, x belongs to closed interval 0. What does it mean? It means that Pn converging to F uniformly on closed interval 0. Okay. Now we'll do what is the corollary of it. I can ask one question on it. Let fx is equal to mod x defined on closed interval minus a to a for some a greater than 0. Thus, there exists sequence of polynomials p and x such that p and 0 is 0 and p and x converge to f uniformly on minus a to a. Is this is true? Yes, it is true. How? Yes, this is true. How it is true? Yes. So we know that f is this, and this is continuous on closed interval minus a to a. Okay. Weierstrass approximation theorem. Weierstrass approximation theorem. There exists Qn sequence of polynomials such that Qn converges to f uniformly on. So Qn converge uniformly to f. It means it also converges point. Then it converges pointwise. Then what is this? This will converge to f0. But f0, what is this? Mod of 0, that is 0. It means Qn0 tends to 0. Okay. Now define p and x is equal to Qnx minus Qn0. Now Qnx is polynomial. Qn is a constant. This implies Pn is a sequence of polynomials. Okay. Now claim. Now we will show that Pn converges to f uniformly. Now uniformly on minus a to a. First of all, check whether our condition is satisfied or not. Whether Pn 0 is 0. This implies define this. Then what we have? Pn0 is nothing but Qn0 minus Qn0. That is 0. So our condition is satisfied. Pn0 is 0. Okay. So our condition is satisfied. Our condition is satisfied. So they will be cancelled out. This is minus sign. So Pn at 0 is 0. Okay. Our condition is satisfied. Now we'll show that Pn tends to f uniformly. Okay. We have Qn tends to f uniformly. Implies करता है there exists n1 belongs to n such that Sorry, 1 minute. Let epsilon greater than 0. Okay. Since Q1 tends to F uniformly, there exists capital N belongs to N such that F x minus Q and X is less than epsilon by 2 for all N greater than equal to capital N and X belongs to minus A to A. Okay. Also, let's say equation number 1 it is also Q and 0 tends to 0 implies that there exists capital N belongs to N such that okay Q and 0 Q and 0 is less than epsilon by 2 for all N greater than 2. From 1 and 2 we have Pn x minus fx. Pn x is q n x minus q n 0 minus fx. This is my Pn x. So I can use triangle inequality here and I can take this and this and use triangle inequality. Okay. This is less than epsilon by 2. This is less than epsilon by 2 for all n greater than. Okay. So before that you put we have 4 and you take maximum of n1 and n2. You take maximum of n1 and n2. Then from 1 and 2 we have 4 maximum of n1 and n2. Maximum of n2. This belongs to natural number. What we have this one. We have that is epsilon for all n capital N and x belongs to closed interval 0. So this implies Pn x minus fx is less than epsilon for all n belongs to capital N and x belongs to 0. Okay. This implies there exists. This implies Pn converges to F uniformly on minus A to A. Sorry, we are taking interval minus A to A. So here I should write here minus A to A. Minus A to A. Minus A to A. Okay. So this question is done. Another question I am taking. That was corollary. Now question I am taking this one. That is also question. Corollary is also question. Okay, you can say question. Now, what about let f is let be a continuous function on AB where AB belongs to real number such that A is less than B. If a to b x to the power and f x dx is 0 for n is equal to 1, 0, 1, 2, 3, and so on, then determine f. Then determine f. Okay. Solution. We have to determine f. You take so okay. Now take. Suppose I have a polynomial. Let px is equal to a naught x to the power m plus a1 x to the power m minus 1. Okay. And so on. a1 x. Okay. A m minus 1 x plus a naught. This is polynomial of degree m. This is polynomial of degree m. Okay. So what about this? A to b, px, fx, dx. When will you open this? I will get this because I can write this a to b, x to the power m, fx, dx plus a1, a to b, x to the power m minus 1, fx, dx, a m minus 1, a to b, x, fx, dx, and a naught, a to b, fx, dx. Okay, I can write x to the power 0 here, no problem. X to the power 0 means 1. Now, this is going n is equal to 0, 1, 2, 3, up to m will be here. M is natural number. Here, in polynomial, m is natural number, degree is m. So, these integrals are 0. It is given, already given. N is equal to 0, 1, 2, 3, up to m, or up to infinity. You can take n is equal to 0, 1, 2, 3, up to infinity. Okay. So, these are integrals 0. So, it means a into 0 plus a1 into 0 plus a m minus 1 into 0, and this is a, am. This is am. So, am into 0. So, what you will get? This is am. Am. This is 0. So, finally, what you got? This is, after solving it, you will get 0. So, this implies a to b, px, fx, dx is 0 for any polynomial p. For any polynomial p. Now, why? Let's say equation number. Weierstrass approximation theorem? Because function is continuous, so f is continuous on closed interval 0. Weierstrass approximation theorem. There exists sequence of polynomials such that Pn converges to F uniformly. Okay. Uniformly on AB. Since Pn converges to F uniformly on AB, this implies P and F into F will converge to F into F, that is F square uniformly on AB. When, because this is continuous function, continuous function on AB. So this implies this is Riemann integrable also. Riemann integrable. Because continuous function on a closed interval is Riemann integrable. This is also continuous on AB. So this is also Riemann integrable. Now we have, if a function in sequence of Riemann integrable function converge uniformly, then F square will be all, then that function uniform limit will be also Riemann integrable, and corresponding integral also converges. Okay. So it means what? It means limit n tending to infinity a to b p n x fx dx is a to b f square dx. Okay. But each part is 0. We already know. Because Pnx is polynomial. Pnx is polynomial. Since Pnx is polynomial, by equation 1 we have a to b Pnx fx dx is 0 for each n belongs to n. Because, okay, so this part is 0. So what is the limit? It means limit n tending to infinity 0 you are taking a to b f square dx. Okay. So this is 0. Okay. So f square x dx. Okay. But f square is a continuous function. Continuous function. And it is non-negative. Continuous, and f square x is nothing but f x square, that is non-negative. It means f square non. Once you have a continuous function which is non-negative and its integral on a closed interval is 0, then the integral the function has to be 0. It means f square x function is 0 for all x belongs to AB. Okay. So this implies f x square is 0 for all x belongs to AB. So this, by taking square root, you get fx is equal to 0 for all x belongs to AB. So what does it mean? If a function is 0 at each point, that function is, it means it's 0 function. So it means f is 0 function. So we have determined function f that is 0 function. Okay. So this question is also done. So today what we have done, we have seen Weierstrass Approximation Theorem and we have proved it, and we have done one corollary on it. You can say that it is question also, and we have done another question that we have to determine f. Okay. Some condition is given a to b x and x to the power n fx is equal to 0, and we determine f. So today's lecture up to this. If you have any problem related to this lecture or session, you can comment me on my YouTube channel. So thank you very much for today's lecture or session. Like, share, comment, and subscribe my YouTube channel. And if you have any problem, you can comment also. So thank you very much for today's lecture. Thank you very much.